Welcome to today's discussion of chance errors in sampling. Before we get started with our formal material, let's take a look at a simple example of sampling and how chance error in just your sampling frame can affect your observed sample. We can here consider that the sampling frame is the picture itself. This is what we're looking at, that's the observation. I have, let's just say, 1,000 observations of the kittens, and this is one. Randomly selected, I don't know. I did want to pick one cute, but here's the point. In this sampling frame, we can see that all 5 kittens are represented with their kitten wrangler number 1, Tiny Tiger. And you might think, well, that looks like the whole picture, right? There's 5 kittens and 1 adult, but there's actually some sampling error here, because if we look at the whole population of the screen or of the area, new sampling frame taken seconds later, you notice there's actually another adult. She's right over here watching them, and we still get the same number of kittens observed, but in this next sample here we've got 2 adults. And the point here is that chance error is always there, even if our sample is just one of 1,000 pictures of kittens and cats who care for them. There's chance error in what your observation is. I know my pictures aren't quite random because I want them to be cute, so I do still have a selection bias for cuteness, but given that all the kittens are cute, we can assume that this is a more or less random picture. And so randomly, we're going to show some part of the frame, some part of the whole population, and not all of it, because there is absent from this population, the mother cat is not here, just my normal cats. And this is a cute illustration of how chance error factors into our observations. And we're going to look at today ways to quantify this chance error. To do so, first we'll look at this example sample based on the survey showed in your the beginning of your chapter. There's a hypothetical discussion here between a sociologist who wants to interview a sample of participants who were in an original large population survey. So and this is loosely based on the National Health Examination Survey. So these numbers do represent the distribution of males and females in the survey, the cross-section they're looking at. And the health study has a representative cross-section of 6,672 Americans. So our total population is all the participants in the representative cross-section of 6,672 Americans. Oh. Yeah. So our population, remember, is the cross-sectional survey. Why is it important that this survey is cross-sectional? Because this cross-sectional survey is, representative, and it's a large survey with several thousand people in it. From within that sample, our example sample is of 100 people who were chosen at random and classified by their sex. In the sample taken from our population, the researcher would like to do interviews with 100 participants, and she wants to ensure that the sample has 46% men, because the original survey had 46% men. And she's got all these other variables to maybe think about, but we're only looking at just the 46 men. Sorry, there's a disturbance here. So our sample, you can see here, is 100 people chosen at random and classified by sex. And here they are laid out. You can see that in this 100 people, 51 were men and 49 were women. In the population, the percentages were 46 and 54. So there's some variance on our sample from the averages in the frequencies in the population. Does that mean that there's something wrong with this sample? No, not really, because remember that the people in the sample are drawn at random. Just by the luck of the draw, you could get too many men or too few if your target is, 46 men, or to approximate the population percentage. Let's say, for example, in another instance, we had took a sample of, we took 250 samples of 100 people from this cross-sectional survey. Because remember, these people have already been surveyed, they're on a list, and we can just use a computer to look at the 100 samples or 250 random samples of 100. This is just like we were doing in a couple chapters ago, taking 100 samples or 100 trials of 50 rolls of a dice. Now we're just taking 250 random samples of 100 respondents. And you can see that each of the percentages of the men in each sample are listed on this table. Some of them are covered up, but the point is that you can see that even though the population had 46% men, there are samples that are above and below 46%. There's plenty of samples that are in that range. Come on then. Please, hurry. And you can see in figure 1 the histogram for the number of men in samples of size 100. So this is the histogram of the number of men in each of our 250 samples of 100 men. Okay, and you can see how it's, oops. You can see how now you see the histogram for the percentages of men in the samples of size 400. There are 250 samples drawn at random. So what happens if we increase our sample size? If we increase the size of the sample, won't it come out more like the population? Well, maybe it will. For instance, as in figure 2, if we increase our sample size by a factor of 4 to 400, we could get another 250 random samples. We can draw almost an unlimited number of random samples from our original population, statistically speaking. So when we do that, if we draw another 250 samples of 400 participants each, The percentage of men is in some of the samples below 46%, in others it's above. You can see from the graph that the low is 39% and the high is 54%. Note also that if you compare the histogram in figure 2 with the histogram in figure 1 above, the sample, multiplying the sample size cuts the likely size of the chance error. Since we multiplied the sample size by 4, it cuts the likely size of the chance error in the percentage by a factor of 2, the square root of 4. Thus, the percentage in the sample, percentage of men, is equal to the percentage in the population plus chance error. One final point is to remember is that our chance error will be different from sample to sample. If you draw one sample randomly, can you say how big the chance error will be? No, you can't say that exactly. You can only estimate how big it's likely to be. We can just get an estimate of its likely size. We can't know ever exactly how big our chance error is. When we look at sample surveys, they involve chance error. And as we discussed when we looked at sample surveys and methods of sampling, we know that introducing probability and the chance process into the sampling process is the most effective way to account for, to control bias. And because we have nice procedures for estimating chance error, it's a very effective model. With this simple random sample, the most basic probabilistic sampling model we've looked at, the expected value for the sample percentage is equal to the population percentage, but the observed percentage will be off due to chance error. Thus, the percentage in the sample is always going to be equal to the percentage in the population plus chance error. Next, we'll look at how to find the likely size of the chance error in a percentage for a simple random sample from a population whose composition is known. In this case, the chance error depends on the size of the sample, not the population. With a simple random sample, as we saw, the expected value is equal to the expected value for the sample equals the population percentage, but expected values are always off by a standard error or so. And so the sample percentage will not be exactly equal to its expected value. How big is that error likely to be? We can find that when we compute the standard error for the percentage. In the example we were just discussing, the sociologist's problem, the standard error is 5 percentage points. In other words, the sociologist should expect the percentage of men in her sample to be off the percentage in the population by 5 percentage points or so. Next, we're going to look at the method for calculating standard errors like this. And generally, the idea is to first find the standard error for the number of men in the sample, then convert to a percent relative to the size of the sample. And the size of the sample just means the number of sample people, like 100 in this case. So first, let's look at a box model for the example sample. You can see here our box model has, our box has the original 6,671, 72. Oh, should have seen that. This is our total sample, and we know it had 3,091 men, 3,581 women. This is the population. Therefore, the box has counts in it, 0, 1 model, where we can label men as the ones and women are labeled as zeros, and there's a corresponding number of tickets that corresponds to the population. Each person in the population gets 1 ticket. From this population, from this box model, we can make 100 draws as we do in this example. And when we do our 100 draws, since we're using simple random sampling, the tickets are drawn without replacement. And we'll look at that as potentially the difference between drawing with or without replacement later on in today's discussion. But first, let's break down this box model. Here we can see that the fraction of ones in the box, we can figure out the fraction of ones, okay? And to help you think through organizing problems like this and earlier problems too, I'm sure it would work, I like to use a organizational method for laying out the procedures, where first we identify our knowns and unknowns, the numbers that we need to know. Because often in statistics problems, in order to get to the final answer, the pathway goes through some additional statistics and calculations. You have to find other values in order to get to your final observation or result. Sometimes I call this just KU. And in this case, our knowns and we know that we're going to need to find our fraction of men in the box, which we can these are going to be easy to find. We'll look at them in a minute. We'll also need to know the standard deviation of the box. And because this is a situation where we have just a big number and a small number, remember that we have a special shortcut for finding the standard deviation when we have a big number and a small number. Ultimately, to complete our box model and the pertinent calculations for this box model, we'll also want to find the expected value and the standard error. Now, I know we don't have we're just working through this as an example. We'll look at a problem in a moment and do a similar process. So first we have the fraction of men. Well, the fraction of men is going to be equal to the number of men in the sample divided by the total sample size. And this is equal to 0.46%, as we know. The fraction of women we could get by either taking 3,581 out of 6,672, or we know that the sample has only men and women in it, so we could also take 1 minus 46%, or 100 minus 46%. So technically this equals 0.46, which would then multiply by 100 to get 46%. To get the standard deviation of the box, we're going to need we need to remember our standard deviation shortcut. So, and that was equal to the big number minus the small number times the square root of the fraction of big times the fraction of small. How does this translate into this problem? Well, big minus small is 1 minus 0 times next the square root of the big fraction. And actually, it doesn't matter if you put these big then small or small then big. They're multiplied, so it doesn't matter. When we put the fractions in here, we could put these actual fractions, or we can put their proportions. I'm going to choose to use the proportional representation. The proportion of the bigs was 54%. That's the proportion of the bigger, sorry about that. So it does matter if you put them in the, it matters that you assess your fractional, you remember to keep your big, that your big fraction relates to the fraction of people, or the fraction of people that had the bigger number. It's not necessarily the the bigger fraction. This is just 1 minus 0 times then the square root of 0.46 times 0.54. And we can then know that our SD is approximately equal to 0.5. Great. So now we know that SD of the box is 0.5. And we can get the expected value of the box. The expected value of men. And we, oops, a moment. Come on. Please, please, quiet. Oh, I'm sorry, folks. We know the expected value. I'm sure you already can see that the expected value of men is equal to the fraction of men. So it's going to be 46%. And our standard error is just the square root of the number of draws times the standard deviation. Technically, this is since we're getting our standard error in percentage format, this is the standard error of the percent. And any standard error, the standard error for the percentage is equal to the standard error for the number divided by the standard error for the sample. So the standard error for the sum of 100 draws is the square root of 100 times our standard deviation, 0.5, resulting in a standard error for the number. I'm doing this in 2 steps. So I'm sorry, I don't know if you can hear the noise here, but it's a bit distracting. So first, we'll get the standard error for our sum, which is our familiar standard error. It's 5. We know the sum of 100 draws from the box will be around 46, give or take 5 or so. If we want to convert our standard error to a percentage, we'll need to take the standard error for the number, in this case the sum, and we divide it by the size of the sample. Oh my goodness. Oh. Times 100. because always to get a percentage, we take our ratio and multiply by 100. 100%. So the standard error for our percentage is the standard error for the number over our sample size is 100 times 100, so it'll be 5%. So in this case, this works out that the standard error for our sum and the standard error for the percentage are the same. Why does it work out that way? Because there's only 100, there's 100 participants. The sample size is 100. Yeah. So this 5% is the standard error for the percentage of men in the sample. Now let's look at one more quick example. We'll do this one a little more quickly. Let's construct a box model for a bigger example sample. So building off the previous example, let's consider a sample size of 400. What happens to the standard error if we increase our sample size to 400? First, let's start by building a box model. Here's our box. How many males and females are in the box? What's the total number of our box here? It's tempting to say that it's 400, but remember, we still have the same box. The box is the population. And our population was 6,672 participants in the National Health Examination Survey. Or actually, it was just the National Examination Survey then. I don't know. Anyway, it was actually the Health Examination Survey when this was done. Same surveys done, changed names over the years. So we have the same box as we did before. We're drawing from the same population. Oh, this is a woman because apparently women all wear skirts. And we still have 3,581 males and 3,091 females. This is our box. From this box, we're going to draw a sample size of 400. We're going to draw So we have our 400 participants. So in our box, we have laid out the population, and now the number of men in the sample is like the sum of 400 draws from this box, right? Because each man is equal to 1, we draw 400 participants and sum the ones. That's the sample, the number of men in the sample. Now we can do our calculations. Oh, there we go. What happens to the first thing we're trying to answer is what happens to the standard error? Well, to figure out what happens to the standard error, we are going to need to find the expected value. And this is the expected value for the sum of our 400 draws. And we're going to need the standard error. So let's figure those out over here. We're consolidating the terms that we're going to use in the future in our knowns and unknowns area. Over in our next section, we can do our analysis. What's the analysis? Well, nothing too scary. It's just the calculation for finding first the expected value for the sum. We know that the expected value for the sum is equal to the number of draws times the average of the box. What's the average of the box? Does anybody remember? To find the average of the box, keep in mind that the men are ones and the women are zeros. So the average of this box is the frequency of the men in the population, which we know was 46%. This is, of course, the average for the men in the box, since that's the question that we're looking at. Note that the average of the box is not the average of the just these two tickets, but of their proportional numbers. So to get the average, we could take the sum of all of the ones. We could sum all the numbers, but remember the zeros aren't going to matter. We sum all of these numbers, and we have 3,581 ones total, and the zeros don't matter in our calculation. So we'll do that over here. The average of the box is 3,581 over the total in our population, 6,672, which is still equal to 0.46 or 46%. So we'll get the expected value of the sum. Our number of draws is 400. And the average of the box, we don't need the percentage in this point. We're just using the proportion because it's the straight average of the box, not the average percentage of the box. Or if we take 400 times 0.46, it's 184. And so that's the expected value of the box, of the sum of this box. Next, let's find the standard error for the sum. Well, we remember that the standard error for the sum is equal to the square root of the number of draws times the standard deviation of the box. What's the standard deviation of the box? Do we need to calculate that again? We don't, because the standard error for the box is the same as the standard error, or excuse me, the standard deviation for the box is the standard deviation for the box. And since we used this same box in our previous example, we already know that the standard deviation is 5. Whoops. Oh no, the standard deviation is 0.5. It's 0.5. We could, if we did need to, if we forgot that we didn't have it, we could easily find the standard deviation again. Remember, it was just equal to big minus small, which is still going to be 1 in any 1, 0 problem, times the square root of the big fraction times the small fraction, or the fraction with the small number. That's how we got 0.5. Thus, the standard error for the sum is the square root of our 400 draws times our standard deviation, which is 0.5, and thus we know that the square root of 400 is 20 approximately, and this is, since this was an approximate standard deviation, times our standard deviation of 0.5, giving us a standard error for the sum of 400 draws. Now we have a standard error of 10. So what happened when we increased our sample size? Well, if we compare this to our smaller sample size of 100, we can see that the standard error went up. Let's also interpret our results for a moment. We know now that the standard error for 400 draws is 10, so we know that the number of men in the sample will be around 184, give or take 10 men. We can easily convert this to a percent. We know that 184 out of 400 is 46%. And so our 184 men out of 400 total in the sample is 46%. And yes, I'm skipping the proportion step here. We're running out of space. And 10 out of 400, but this is the expected value as a percentage. And we can get our standard error as a percentage too. That's just equal to 10, because remember, our standard error is in the same units as the expected value. So our standard error is 10 men out of 400 total in the sample. So the percentage is 2.5%. So we can now say that with a sample size of 400, the percentage of the expected percentage of men is 46%, give or take 2.5%. Finally, let's look at one further example here. We can apply the normal curve to this model and find the probability of drawing a sample with 45 or fewer men. How can we do that? Well, first thing we're going to need is a little bit more space on our page. So let me do that for us. Oh, shoot. Oh, I'm going to just make this all smaller so we can still see it if we need some of this information. And I did, oops. I forgot we were using a sample size of 400 here. So let's find the probability of drawing a sample with 175 or fewer men. So it's just a small additional step here to apply the normal curve to these data and find the probability of drawing a sample with 175 or fewer men. First, we need to convert 175 to standard units. So we already know many things about this box. So we can use these knowns to help us answer the question of the probability of drawing a sample with 175 or fewer men. Our first step is to convert 175 to standard units. And so standard units are a z-score. And so this is going to be the z for our oops. We'll just call it the z of 175. Then it's equal z. Converting to standard units is always equal to some model of the observed value minus the expected. We previously looked at the expected value as the mean, but here we're talking about sums. So this is observed value minus the expected value. divided by our standard error. Thus, convert this to standard units. We want to know about this observation, the chances of observing 175. So that's the z-score we're looking for. We already know our expected value is 184. And the standard error is 10. Thus, 175 minus 184 is negative 9. Over 10. Which simplifies to a negative 0.9. I should have made that 174. In fact, let's do that. Let's just make a real-time edit here for the sake of easier mathematics. And we'll make this 174. Why do I want to make this 174? Does anybody have an idea of why that's going to be more convenient statistically for us? Or mathematically, rather? And statistically. What happened here? Oh. Because then it will become -1, exactly. And if it's -1, then that's one standard unit. We already know the proportion of the population that's at one standard deviation above and below the mean, right? And so this makes it a lot easier. I'll draw our figure over here. So we can draw a normal curve, and we remember that our expected value is 184. In standard units, that would be 0. 174 is one standard unit below the expected value, so that's a -1. And to answer this question, we want to know the probability of drawing a sample with 174 or fewer men. Then that's the probability that is outside of this portion of the distribution, right? We know that within one standard unit is going to be 34%. And that below the mean in total is always 50%, right? And there's 50% on the other side. So to get this proportion here, we can take 50 minus 34. And we know that is 16%. So there's a 16% chance of drawing a sample with 174 or fewer men. Does everybody see how we can continue to use the normal curve? And we can do this because these are normally distributed data, but there are many, and if they weren't normally distributed, then finding this probability would be really outside of the scope of this class. But the important thing to remember is that we have various applications of the normal curve. But when you're doing problems that are related to using the normal curve, you generally follow a pretty similar process of binding. First, we got z-scores by taking the x minus the x bar, or a particular observed value minus the mean. But that's basically the same model that we've used here, except we're talking about an observed value of, for a whole sample, minus the observed value, the expected value, and dividing by our standard error. And the reason we use the standard error here is because, again, we are considering a large sample. So we're looking at, we need to account for the sample size as it relates to error. And so it's as simple as that, using the normal curve. We have just one final main topic here, and we're just going to look at the correction factor briefly, because there's a lot of mathematics behind the use of the how the absolute size of the sample determines the accuracy of percentage estimates and not the size relative to the population. But I'm going to skim over that mathematics because we really want to get to the end product observation here. But let's just do a brief treatment of thinking through why this is true. So that the absolute size of the sample determines the accuracy of the percentage estimate, not just the size relative to the population. But that's true only when the sample is a small part of the population. And this is generally the case. So generally we have a small portion of the whole population, and the number of draws is just a tiny fraction of the number of tickets in the box, or the number of total people in the population. When we take the draws without replacement, it barely changes the composition of the box when there's thousands and thousands of people in the box. And so on each draw, the chance of getting a 1 is still very close to 50%. And it's similar for the chance of getting 0. As far as the chances are concerned, there's almost no difference between drawing with replacement and drawing without replacement. So essentially, that's why the size of the population has almost nothing to do with the accuracy of the estimates. The sample size is what's really the determining factor of our accuracy. However, if the sample is a substantial fraction of the total population, then a correction factor must be used. This is likely to happen when we have maybe a smaller population, and so you end up sampling a larger fraction of that population. Thus, you can see that the correction factor itself is equal to the square root of the number of the tickets in the box minus the number of draws divided by the number of tickets in the box minus 1. And this idea of the number minus 1 is one we'll see echoed in some later statistics we look at too. Note that when the number of tickets in the box is large relative to the number of draws, the correction factor is nearly 1. Let's say there's 7,000 tickets and only 100 draws, then the numerator in this formula would be 7,000 minus 100, or 6,900 over 7,000 minus 1, or 6,999, and this is very close to 1, the square root of this whole thing. So we don't need to use the correction factor for these when we have just a sample that's a small fraction of the population. Consider, however, if we had a population of only 100 and we sampled 80 people from it, then we would end up with a much larger fraction of the population, the total population sampled. And that's when you would want to use the correction factor. In summary, the sample is only a part of the population, so the percentage composition of the sample usually differs by some amount from the percentage composition of the whole population. In probability samples, the likely size of the chance error is given by the standard error. We can use a box model to find the standard error. And when the problem involves classifying and counting, or just taking percents, then there's only ones and zeros in the box. And we can use our standard deviation shortcut. When you're drawing at random from a 1-0 box like that, the expected value for the percentage of ones in the sample is simply equal to the percentage of ones in the box. To find the standard error for the percentage, you can first get the standard error for the corresponding number and just convert it to a percent. Finally, remember that when the sample is only a small part of the population, the number of individuals in the population has almost no influence whatsoever on the accuracy of the sample percentage. It's down to the absolute size of the sample that matters in determining the accuracy of the percentage, not the size of the sample relative to the population. When we consider our sample size, we know that the square root law is exact when the draws are made with replacement, but when they're made without replacement, the formula still gives a good approximation as long as the number of tickets in the box is pretty large relative to the sample size. And in the event that we have a sample size that's large relative to the total population, then you can use the correction factor to get the exact standard error. We could consider ourselves to be using the correction factor all the time, but remember, when our sample is very small relative to the population, the correction factor is almost equal to 1, and so multiplying by the correction factor of 1 doesn't affect our end products, and we just don't normally see it in that sense. Chance error is an inevitable part of any sample survey, and it's very important that we estimate our chance errors as accurately as possible. Remember that the procedures we talked about today are only relevant when you have a normally distributed, a normal distribution that applies. If the distribution isn't normal, then again, you'd look at some other procedures and a whole nother lecture topic. Next, we'll take a look at some of our exercises for this chapter.